this video, we're going to do a detailed walkthrough of our recently launched reference design kit, using our innovative ionomer amine polymer membranes and its application in designing of AEM water electrolyzers. Our revolutionary polymers unlock performance, stability, and reliability, results not seen in the market, and has been enabling those who are leading the way. The future of the hydrogenicom testing setup is time-consuming and often costly. This video is intending to walk through each step of the process and unleash the power of our amine membrane and polymer. This will include showing you each of the components that comes with the kit, how to pre-soak the membrane properly, and how to set up the electrolyzer for your intended design experiment or validation. Today I'll be showing how we assemble our 5 square centimeter water electrolysis cell using an amine membrane. The membrane should be exchanged prior to cell setup.
So this is simple, just remove the membrane from the backer, place in the solution. It should be pretty easy to remove the membrane from the backer. You can also take the entire membrane with the backer and submerge it in the solution. The backer should unpeel from the back of the membrane. Here I'm showing a membrane being moved from 1 molar potassium chloride solution to 1 molar potassium hydroxide solution. To do that, I'll take my membrane that's been soaking in 1 molar potassium chloride. I'll remove the membrane and give it a quick rinse with DI. And place it in the 1 molar potassium hydroxide solution. Note that once the membrane is in potassium hydroxide and has been exchanged to the hydroxide form, the membrane should not be in contact with deionized water. Also, once the membrane is soaked, it should not be dried. Our cell hardware consists of 4 nickel plates. These plates are solid nickel. All O-rings are EPDM, ethylene propylene diene monomer rubber. These O-rings are stable in potassium hydroxide and very caustic conditions, but we find that we still need to change the O-rings, particularly on the anode side, more frequently. Stability may be reduced in oxygenated potassium hydroxide. The anode GDE that we're using is nickel felt spray-coated with nickel iron oxide. The GDE we're using on the cathode is carbon paper spray-coated with platinum on carbon. We use a die and hydraulic press to cut the GDEs and the gasketing material. Our gaskets are PTFE sheets and are non-compressible. Gasketing thickness is chosen based on desired GDE compression. Right now we're compressing our anode and cathode GDEs to between 9 and 10%. Cut the gaskets and the electrodes using dies and a hydraulic press. This is for cutting the GDEs. This is for cutting gaskets. When we cut the materials, it's important that we cut them in such a way that no sharp edges are pointed towards the membrane. So you can see here, when we cut this electrode, we're cutting it with the die facing the active area and the catalyst, so that if there's any deformation, those fibers are pointed away from the membrane surface. Similarly, when we're setting up the gasketing material, we look at the edges of the gaskets along the active area and set it up so that these gaskets have no sharp edges pointing towards the membrane. Here is a drawing of our cell assembly, showing gasketing materials, GDEs, nickel plates, and our membrane. We use these 2 pins to help align the nickel plates and gasketing to make sure that there's no movement or misalignment during the setup process or when we move the cell. Next, I'm going to take the membrane that's been soaking for at least 1 day in potassium chloride and 1 day in potassium hydroxide, and sandwich that between our electrodes and gasketing. I'm not drying the membrane before I put it in the cell. It's important that the membrane is still hydrated. And I'm going to add this gasketing, again, making sure that it's aligned such that there are no sharp edges pointing towards the membrane.
It is important that the membrane lay perfectly flat across the plate to prevent wrinkles or folds.
Slightly different thicknesses for the anode and cathode gasketing because our electrodes are slightly different thicknesses. And we want to keep our compression, like I said before, to 10%.
If electrode compression is too high, you may observe damage to the membrane and measure high gas crossover. If compression is too low, you may see increased ohmic losses because the porous transport layers aren't making good contact with the flow fields.
This is our cathode. This is the spray coated paper. Next, I'm going to secure the cell using these two O-rings. They don't provide the pressure that we need to hold the cell, to compress the cell, but they do hold the plates in place. Now this is ready to place in our test stand. As you can see, the plates are lined up in the cell hardware. The bottom of the cell fits over the anode side tubing, which fits through the current collectors on the bottom of the hardware. Our hardware is pressurized to 160 psi. This is an alternative to using screws and a torque wrench. The 5 square centimeter cell comes with a pneumatic bladder compression system for even compression of the electrodes. It's recommended to close the cell with a maximum 160 psi of pressure on the bladder, which translates to 350 psi of pressure on the active area. The 50 square centimeter cell does not come with an integrated bladder compression system. Therefore, it's recommended to be closed with the assistance of a hydraulic press by applying the load specified here to ensure even compression across the cell. It's not recommended to compress the cell by tightening cell bolts in a typical star pattern using a wrench without a press or bladder system because it can cause uneven compression. Now that the cell is in the hardware, I'll turn on our solution, which is 1 molar potassium hydroxide, flowing to both the anode and cathode at 5 mils per minute. So that's approximately 1 mil per minute per centimeter squared. Once solution has entered the cell, I'll turn on the temperature to 80 degrees Celsius. Here you can see our connections to our power supply unit. We have separate cables for applying current density and sensing the voltage. Here are the connections to our potentiostat. On the anode, we're connecting the working and working sense electrodes. On the cathode, we're connecting the counter electrode and reference electrode. Here is a diagram showing the power supply and potentiostat connections. Your test reads will vary, but refer to our reference design application note to know where nominal is.